Hello, everyone. Welcome back. We are again towards the end of chapter 3. We're not going to talk about some of the geometric things we can do with the integral. We're going to start with the area between two curves. And our main formula that we are looking at here is here. And I know it's a little small. Let me blow that out a little. And it's basically the integral of the top function minus the bottom function. And the easiest way to view that is to make at least a vague graph of what it is that we're looking at. And so we have Farmer Jones and his wife, Dr. Jones, decide to build a fence in their field to keep the sheep safe. Since Dr. Jones is a mathematician, she suggests building fences described by y equals 3x squared and y equals x squared plus 9. Farmer Jones thinks this would be a much harder to build than just building with straight sides, but he wants to make his wife happy. What is the area in the enclosed region? I'm going to use a bigger sheet of paper here, just so that we have more space. There we go. All right, and so let's write down our functions first. This is our first example. Y equals 3x squared, and y equals x squared plus 9. I'm going to vaguely draw these, just so we get an idea of what it is that we're looking at here. And our first function is going to shoot up quite quickly. That's going to be here. It's going to do this and this. Whereas if we were up here at 9, this graph is going to be much fatter. And it's going to cross out here. And the idea is we need to start out by finding our boundaries of integration, and that's going to be where these two intersect. So we're going to start by setting these two equal to one another. And subtracting the x squared to the other side, I get 2x squared equals 9, and x squared equals 9 halves. And I'm going to go take the square root. Now, this is going to give me plus or minus 3 over root 2. And to be clear, that means that we are here and here. And the area of interest is going to be all of this. I'm going to cheat a little bit. I'm going to actually only integrate from 0 to 3 over root 2, and I'm going to double that area, and that'll give me that left side of the area. This is what's called an even function, so we're allowed to do something like this. I won't get too in depth with that. But what I'm going to do is set up my integral, and it's going to be the top function, which is the purple, and I'm going to double that. So this is this over here. So area is going to be double the integral, and I'm going to start from 0 to 3 over root 2 of the top function, which is the x squared plus 9, minus the bottom function, which is the 3x squared. And top function minus the bottom function is going to give me the orange. Now I'm only going in the orange that has the double strikes in them. And then I'm doubling that. That's what the 2 out in front represents. And notice I'm starting at 0. So this is going to give me 2 times the integral 0 to 3 over root 2 of negative 2x squared plus 9 dx. And let's now integrate. This is going to be 2 times. This is going to be negative 2/3 x to the third power from 0 to 3 over root 2 plus 9x from 0 to 3 over root 2. And let's go ahead and plug all that in and work out the algebra a little bit. And this is 3 over root 2 cubed minus 0, so I'm not going to bother writing that in, plus 9 times 3 over root 2 minus 0. So again, I'm not going to bother writing that in. And let's keep going over here. This is going to be 2 times. This is going to be negative 2/3. 3 cubed is 27. Root 2 cubed is going to be 2 root 2 plus 27 over root 2. And I'm going to notice that I can do some reducing. Oops, let's go there. And this is going to give me negative 9 over root 2 plus 27 over root 2. And that's going to be 2 times, and that's going to be 18 over root 2, or 36 over root 2. And we could stop there, but I'm going to actually rationalize the denominator. Oops. Or 18 root 2. All right. So to me, the algebra part of this is the most amount of work. The actual calculus part is the relatively simple part. Let's move on to our second example here. Part 2 says, sketch the region enclosed by y equals 7x and y equals 2x squared. And our graph is going to look here. And we are going to end up with a straight line with a relatively steep angle and part of a parabola that's also relatively steep. And the area of interest is going to be here. And to be clear, the blue function, the 7x, is actually on top. When we're talking about which one's on the top, which one's on the bottom. All right, so let's find their points of intersection. So 2x squared equals 7x. A common factor of x out. This is going to be x equals 0, x equals 7 over 2. So this here is 7 over 2. So those are our boundaries. And once again, the top function is the line. We don't have symmetry like we had before where we can cut it in half or anything like that. So this is just going to be from 0 to 7 halves. 7x minus 2x squared dx. So I'm going to go ahead and integrate that. That's going to be 7 halves x squared from 0 to 7 halves minus 2/3 x to the third from 0 to 7 halves. All right, so we're going to get 7 halves times 7 halves squared minus 2/3 7 halves to the third power. All right, let's see what we end up with here. So that's going to be 7 times 7 squared. 7 times 7 squared in the numerator over 2 times 2 squared. I didn't put the zeros in, by the way, because 0 squared is 0, and 0 to the third is also 0. So this is going to be 2 times 7 to the third power, 2 times 7 raised to the third power, 686 over 3 times 2 to the third power. And now I need a common denominator of 24, which means I'm going to have to multiply this by 3 over 3. Oops. 0.29 over 24 minus 686 over 24. So 343 over 24 is my final answer. Now, you might see some other algebraic ways of doing this, or don't break it up into two separate integrals like I did. Whatever works for you, that's fantastic. For our next part, we're going to get into volumes of rotation. And I want to go back to our part here. So we start with an area, and here's our area of our function f of x from a to b. That's the left graph. And we are going to take each individual tiny little snippet, and what we're going to do is we're going to whip this around the x-axis. And it's going to form a disk, a circle, of radius, in this case, y. So to be clear, we're going to end up with a disk with a radius of y, meaning y is some function of x. And for this course, we're only going around the x-axis, which is nice. In other ones, we end up going around the y-axis. We end up with functions where x is described as a function of y, which gets even more confusing. And then sometimes it's not even around an axis, it's around some line. But we're going to keep ours nice and simple. The volume of the solid rotating is going to be, and we can see that the area of a circle is pi r squared. In this case, that's our function squared. And then you can see our actual formula here, which is pi r squared or y squared or f of x squared. It all means the same thing. All right, so we are now here. And once again, I'm going to go back to my scratch paper. It's just a lot more space. And we are going to start with, we are going to take, this is example 3. And we're going to take the function f of x equals the square root of 100 minus x squared, which the graph of this, very nicely, is just a simple circle of radius 10. We're going to go around the x-axis from 2 to 10. So let's get an idea of what graphically this is going to look like. So we have our graph is a circle. In this case, it's the top half of the circle because it's the positive root 100 minus x squared. And we're going to be going from 2 to 10. So our area of interest that we're rotating is there. And we are going around the x-axis. So we're whipping around the x-axis. And what we're going to generate for every single little piece here, nope, I don't want a straight line. I want a disk of radius y. So I'm going to draw that over here. And this means that our radius of this circle is the square root of 100 minus x squared. That's y. So our volume of rotation, and I won't get too into the calculus here, and we're going from 2 to 10 of pi r squared. And here is our integral. Now pi is a constant relative to everything, so I was pulling it out. And I noticed that the squared and the radical are going to cancel out. And now I'm going to actually integrate. So let's punch all that together. All right, so let's see what we get here. So this is going to be 800 minus 1/3 times 1000 minus 8 is going to be 992. "992 is not a multiple of 3. No. So we're going to have to get a common denominator. So this is going to have to become 2400 over 3 minus 992 over 3. So 2400 minus 992 gives us 1408 over 3 times pi. And like it or not, that is our answer. Now we could get some sort of a decimal approximation by dividing that and multiplying by pi and stuff, but typically in a math class, we like to leave things in exact form if possible. All right, let's keep going. Our next example is find the volume of the solid obtained by rotating the region bounded by y equals 7x squared, x equals 1, x equals 3, and y equals 0, and we're going around the x-axis. Now remember, y equals 0 is the x-axis. So let's see, we have a parabola, get an idea of what we're looking at here. And we are getting the idea, we have a big outline of a parabola. I'm going to over-exaggerate it a bit. I'm only going to do the right-hand side because we're only going to be dealing with from 1 to 3. And we are going to be looking at this enclosed area here. And that is going to be rotating around the x-axis. So we're going to be getting a whole bunch of disks of radius y, which to us means seven x squared. So our area is going to be the integral. I'm going to pull the pi out for the pi r squared from 1 to 3 of 7x squared squared dx. So there we are. I pulled the 49 out just to, again, I like pulling those constants out when I can. And this is going to give us 49 pi over 5 x to the 5th from 1 to 3. This is going to be 3 to the 5th minus 1 to the 5th. Now, to be clear, 1 to any power is always 1. 3 to the 5th, I'm not totally sure what that is. So let's see what that is. So 3 raised to the 5th power. Okay. So we're going to get 49 pi over 5 of 243 minus 1. So 49 pi over 5 times 242. So 242 times 49 divided by 5. So we're going to get 11,858 over 5 times pi. Again, we'll leave that in exact form. Makes it just a little bit easier to deal with. So hopefully we're starting to see some patterns here. It's nothing too complicated. Again, we're very fortunate this is not a regular calculus class. This is actually 2 full sections, and it gets much more complicated. Part 5 says, find the volume of the solid form by rotating the region enclosed by y equals e to the 4x plus 5, y equals 0, x equals 0, and x equals 0.9. Okay, so let's kind of draw this. And this graph is actually going to look like this. It's going to be way up here. It's going to cross at 6. And it's going to shoot up like that. This is at 6. And we are going from 0 to 0.9. So our area of interest is here. And once again, we are going to end up with rotating each of these around the x-axis with a radius of y, which means to us, we're going to be here with a radius of e to the 4x. So our area is going to be pi, the integral from 0 to 0.9 of e to the 4x squared. Oh, I forgot the 5. Hang on. Plus 5 squared dx. Shoot, I forgot that plus 5. That's going to make it a lot more complicated. All right, we are going to use a rule. Let me just reiterate, we have a rule that says a plus b squared is here, where a in our case of our integral is the e to the 4x, b is the 5. So I'm going to go ahead and FOIL that out. E to the 4x squared is e to the 8x plus 2 times 5, so that's 10 e to the 4x plus 25 dx. And in a previous video, I mentioned that when we integrate e to the constant times x like this, we end up with 1 over a e to the ax plus c. A is going to be, in our case, the 8 and the 4 when I actually integrate it. So we have pi. We get 1/8 e to the 8x plus 10 over 4 e to the 4x plus 25x. And each of these are going to be evaluated from 0 to 0.9. And from 0 to 0.9. All right. Well, let's keep going. This is going to get ugly. A little ugly, just because we have decimals and fractions. 1/8. This is going to be e to the 8 times 0.9. That's going to be 7.2 power. 8 times 9 is 72, but we have the extra decimal in there. Minus e to the 0 power, which is just 1. 10 over 4 reduces to 5 halves. And we are now at e to the 4 times 0.9 is the 3.6 minus e to the 0, which again is 1, plus 25.9 minus 0. All right, let's see what we get with all of this. So pi over 8 e to the 7.2 power minus pi, e to the 0 is 1 over 8. Plus 5 pi over 2 e to the 3.6 power minus 5 pi over 2, because that's just 1 there. And 25 times 0.9 times pi. 25 times 0.9. So this becomes plus 22.5 pi. All right, so let's clean this up a little bit if we can. So negative 1/8 minus 5 halves plus 22.5. So let's do this. Negative 1/8 minus 5 divided by 2 plus 22.5. Oops. And turn to a fraction. So that's going to give us pi over 8 e to the 7.2 power plus 5 pi over 2 e to the 3.6 power plus 159 over 8 pi. We could probably clean that up a little, but I think we're good. So I'm just going to leave it like that. All right, and that brings us to the last part of this section, which is finding the average of a function. And I'm going to switch back to our other screen. And so we have the average value of a positive f of x, and we have a nice geometric interpretation. And what we're looking for is the average height. That's the capital H that we see here, right there. And it looks like b minus a is going to be with us here, times the height, is going to give us that area. And we know the area. Anyway, long story short, we don't need to get into all the fanciness of it. Oops, but we end up with this here, which is our actual formula, which is here in the bright yellow. So to find the average is just the integral, and then we do the 1 over b minus a in front of it. I'm avoiding all the mathematical reasons why, but it's actually kind of cool, but I'm not going to bore us too much with it. So we want to find the average value of this function. So b minus a in this case is 4 minus 0, or 4. So the average is going to be 1 over 4 times the integral from 0 to 4 of 2x to the third power dx. And I'm going to pull that 2 out in front. Actually, let's just do this. 1/4 times 2 times 1/4 x to the 4th power from 0 to 4. And we can see all those constants. We end up with 2 over 16, which is 1/8. And then we get 4 to the 4th power, which I believe is 256. 4 raised to the 4th power. divided by 8 is 32. So what's the average of this function? It is 32. And we're going to do one with compound interest. Now, if we want to recall, our compound interest formula is here. Suppose you deposit $7,000, that's our principal, at an interest rate of 0.05, compounded continuously, that's the E part. Find the average value of your account during the first 2 years. So T is going to go from 0 to 2. So our average is going to be 1 over 2 minus 0, the integral from 0 to 2. And I guess I should do this. So our function is going to be 7,000 e to the 0.05 times t. So there's our function with respect to t. Here we are. So that becomes 7,000 divided by 2. That's going to be 3,500 of e to the 0.05 t dt. And remember our rule from above, that we're going to get an extra 1 over 0.05 there. So 3,500 over 0.05 e to the 0.05 t from 0 to 2. Remember, e to the 0 power is 1, not 0. And 3,500 divided by 0.05. I hit the wrong button, sorry. 3,500 divided by 0.05, 70,000. And this becomes e to the 2 times 0.05 is 0.1. 0.1 minus e to the 0, which is just 1. And so let's figure out how much money that actually is. So let's take 70,000 times e raised to the 0.1 power. I use the right arrow to get out of that, the exponent, minus 1. So it looks like this becomes about, our average amount in this account is going to be about $7,361.96. Not too difficult. Some of the algebra gets a little intense, but it's really not too bad. All right, I'll see you next video.